Hello everyone, I'm Zhengchen Hong from the Department of Statistics and Information Science, student ID C22402. Today I am presenting my data mining final project on the Taiwan lead pig transaction market. Our dataset comes from the National Open Data Platform, provided by the Ministry of Agriculture. This data contains market transaction records of live pigs in Taiwan, named PIG.CSV. It is a structured table consisting of 9,999 entries and 38 original variables. Our primary target variable is the overall average price of traded hogs. Variable definition. Here we define key features including standard Gregorian dates, mark names, month, day of the week, and weekend indicators. There are zero missing value in the raw data, but the defensive pipeline is built to automatically fill future missing entries using cluming medians to resist outliers. The objective of data cleaning is to enhance quality and eliminate noise to prevent overfitting. We remove redundant subcategory features that overlap with core metrics, convert mingled date to standard Gregorian format, and extracted seasonal variables like month and weekend. In a decision tree model, no discretization was applied to continue independent variables, since the algorithm nature, naturally identifies optimal split point, feeding raw value directly preserves full information and enable sharper binary decisions. The answer is yes, recording was applied. Since Python decision tree implementation cannot natively process raw text strings, we utilize scikit-learn label encoder to make text value like market name into distinct integers starting from zero. Our experiment re- revealed that when mean sample split dropped from 0.03 to 0.02, the tree split too deeply. As a result, training accuracy continues to rise while testing accuracy stagnates and drops, which is the textbook definition of overfitting. We compare two feature selection methods. Chi-square tend to select large-scale volume indicator, yielding lower lower test accuracy, where model selection directly target highly relevant price indicator, boosting test accuracy to 69.55%. The final comparison showed that retaining all variable, delivering the absolutely high highest testing accuracy of 997.95%. This indicates that subcategory volume across web classes contain no negligible trending signal, and keeping all future features provide the most robust model. Though constraint tuning are recommended, final tree sus- successfully converge within 7 layers, utilizing only 39 total nodes and 20 leaves. It flawlessly segmented thousands of records, achieving a 97.70% text accuracy and striking an ideal trade-off between complexity and precision. The extract rules are highly intuitive. If non-freezing plate prices are small than 95.60 and small equal 95.01 and standard hog price is small equal 98.01. The day is classified as low price. Otherwise, it satisfies the criteria of a high price market. To verify stability, we execute a five-fold cross-validation. The dataset was divided into five subsets. The highest accuracy reached 99.60%, yielding a spectacular mean CV accuracy of 97.671%. This consistency proves our model is exceptionally stable. Association. For association rules, continued feature would convert into category bins. Since market-based kit analysis deals strictly with taxable labels, smooth is invalid here. Thus, we implemented random oversampling to balance the minority price surge data. Association rules uncover strong supply effect. Rule 1 shows that if there is a small trading volume, there is a 69.99% confidence that price surge bigger than 30.95 with a lift of 1.29. Rule 2 shows heavy hawks also strongly correlate with high price. Moving to the SVM model, no manual discretization was applied because SVM relies on spatial margin to classify data. Preserving continuous forms allows the algorithm to capture complete geometric variance and compute precise distance metrics. For the target variable y, we apply binary encoding based on the 95 TWD result. This fit SVM binary classification architecture perfectly, enable the model to establish clear decision boundaries in high-dimensional space. For nominal feature variable x, we use one-hot encoding. This avoids spurious ranking introduced by label encoding, allowing the distance-based SVN to accurately reflect geometric differences between independent categories. Yes, standardization was strictly applied. We employed standard scalar to normalize all numerical input, preventing large-scale variables like trending volume from dominating the geometric space and ensure equitable distance measurement. Under a fixed split of test size 0.2, our support vector machine classifier performed exceptionally well, achieving a final testing accuracy of 95.90%, demonstrating strong predictive power in high-dimensional space. Experimental data revealed a massive contrast when linear SVN stagnate around 71 accuracy, switching to a non-linear RBF kernel with C equal 10 triggered a performance leap to 95.90%. This strictly proves that hog market dynamics are fundamentally non-linear. In the random forest model, manual discretization was omitted, since tree-based ensemble accuracies naturally determine optimal split point during construction. Avoid arbitrary being ensure that algorithm preserve the full spectrum of feature variants. The target variable "y" was recalled using binary encoding, based on the 95 TWD result. This fit random forest classification architecture perfectly, allowing the tree to precisely calculate node pairing via Gini impurity. Nominal variable here were also recording use one-hot encoding instead of label encoding. This prevent This prevents random forests from introducing a false order to categorical variables, helping the model learn feature more accurately. The answer is no standardization was applied. Random forest is a tree-based algorithm that possesses scale invariance. It evaluates only the relative order of feature values during node splitting rather than absolutely spatial distance. In the baseline testing of our random forest model, test size equal 0.2, the model demonstrated the true power of ensemble learning, achieving a high test accuracy of 96.35. We compare four distinct configurations using vary number of estimator of 10 to 300, although configuration 2 and 3 yield slightly higher test score. That's 100% training score indicated served overfitting and high generation risk. We officially recommend configuration 4 with 150 estimator and a max depth of 8. It introduced structure constraints, building training accuracy at 96.92% and test accuracy at 96.20, with a minimal gap of 0.72%. It ensures robust generation. Entering the K-nearest neighbor model, no manual discretization was applied, because the K-n classifier operates by calculating spatial promises via Euclidean distance. Manually categorizing this input will cause geometric relationship and cause information loss. The target variable "y" was binary encoding to provide this create class label required by KNN. Feature variable "x" were all recalled use one-hot encoding to prevent distortions in spatial intervals, ensuring accurate distance calculation. Yes, standardization was mandatory here, since KNN relies entirely on geometric distance metrics left under stem lines. Large range features like trending volume would completely demonstrate smaller scale features like width. Standard scalar ensure incredible feature contribution. This page details our KNN multi-configuration experiment. By scanning various neighbor sites, the model optimized at k equal 27, securing a test accuracy of 94.95. We then applied a soft voting classifier to assemble our best random forest and KNN model together. by weighting prediction probabilities rather than row counts. This ensemble pushed test accuracy to 96.55% and minimized the overfitting gap to a more 0.10%. This is a voting code and voting trend test accuracy comparison. This page is K-means code and tuning to unsupervised learning. We utilize K-means to discover the market natural groupings based on the WCSS, able plot, and silhouette coefficient. The data family supports K equal 4 as a final configuration, reduce error by 42.18 compared to K equal 2. This page is silhouette coefficient. This page analyzing the numerical profile and business label of our four final clusters. Cluster 0 consists of 2,755 entries, featuring highly stable trending volume and steady baseline price. And Cluster 1 hold 3,091 entries, characterized by significantly heavier hawk width and higher premium price, making it top target for processing plays. Cluster 2, the largest cluster with 3,462 entries, where trading value spiked alongside a massive price surge. Class 3 contains only 694 records, represent extreme, sparse market anomalies typically seen on holiday eves. On this page, we validate the K-means clustering result via ground truth mapping by mapping cluster 0 to label 0 and cluster 1, 2, and 3 to label 1. The resulting classification accuracy is 94.44%. This high accuracy demonstrates that the K-means spectral clustering heavier, aligned with accurate hog price movement label, yielding robust discriminative power. The ultimate showdown reveals that K-means majority voting machine win with a stunning 99.62% accuracy. This result indicates that the dataset exhibits highly comprehensive geometric clustering characteristics. Make the clustering first, collective voting second. Framework acts as an apathetic noise filter to perfectly capture market patterns. Thank you.